This lesson will teach me to apply the exponent rules to simplify an expression or store problems. In particular, the exponent rules in this lesson deal with something called rational exponents. What's a rational number? A rational number is a number that can be written as a fraction. So a rational exponent is an exponent that is a fraction. This fraction will generally be an improper fraction, 1/2, 3/2, but it won't be in the form of a mixed number. And it won't be a decimal. If it's going to be something like 2.5, we use the fraction 5/2. What is a radical? A radical is essentially the square root symbol. We've seen this symbol in other forms. We know that this is referred to as a cube root. This one is referred to as a square root. So this particular symbol here, even though we call it a square root, it's really referred to as a radical. Fun fact, if you think about the square root symbol, its purpose is that it undoes a square. So if you had a problem, for instance, x squared equals 9, and you wanted to undo the square, if you would square root both sides, you'd undo the square. The reason why this particular symbol is called a square root in this case is because it's undoing a square. There's essentially a little teeny tiny 2 hiding here. Just like the teeny 3 was written in front for a cube root, there's really a tiny 2 written in front. Just like when we take any number and we don't have to write the number under 1 or the 1 under the number, or when we take a letter like X, we know that there's 1 in front of it. This 2 isn't written for the same reason that we don't write the 1 and we don't write the 1 in both places, because we're assuming that whenever we see just the symbol as a square root, if I want to make it a cube root or a fourth root or a fifth root, I'd have to put that number out in front. So ultimately, what is a radical? It's that kind of check mark like symbol that is used in roots. All right, rules. These rules convert rational exponents, meaning fractional exponents, to radical expressions and vice versa. They are interchangeable. The first one takes a rational exponent where the fraction is 1 over any number, we're going to use n, and it puts it into a form that is a radical. The n goes out in front, and the 1 is essentially on the x, but we don't have to write it. The other version is where the number up top is not a 1, so we would again write the radical symbol, the x goes inside. That n is on the outside, it's referred to as the index, and the m goes on the inside. I had a student one year say that they remembered this rule by the phrase, you have to go downstairs to get outside. Let me write that down. Go down stairs to get outside. So if you're on the second floor of a building and you need to go outside, you go down the stairs, downstairs to go outside, downstairs to go outside. Convert the expressions to radical form, simplify if possible. Downstairs goes outside, so this is going to be a fifth root with the third power on the inside. Notice here, 5 times x to the 1/3. The 1/3 is essentially only touching the x, so the 5 is just a normal 5. The x is in the radical, and you have to go downstairs to get outside, so the 3 is on the outside. In this particular problem, the 1/2 is touching everything because of the parentheses. So it's the square root. You have to go downstairs to get outside, so the 2 is on the outside. And here, the 16 and the b are both underneath, and there's a 1 here, but we don't have to write it. The idea of simplify if possible. Do you know what the square root of 16 is? I sure hope so. The square root of 16 is 4, but I can't take the square root of b. I don't really know what that is. So it's going to stay a b. All right, next problem. There's kind of a lot going on here. This one was harder than what I had originally anticipated. The negative 5y squared times, So this is all just going to stay put for a second. Negative 5y squared times, just like in letter C, I have parentheses, downstairs to get outside, so that's a 2, that 4x, all to the third power. Now it may seem kind of strange, but grab your calculator and see what that is regarding the 4. When I typed that in my calculator, I ended up with 8. So it's negative 5y squared times, when I did the square root of 4 to the third power, I got 8. But I really can't take the second root of x to the third. Kind of using the exponent rules that we've worked with before, the 5 and the 8 are normal. Y squared 2x to the third. This one is pretty darn complex, way harder than what you would ever see on a quiz or a test. All right, convert each expression to rational form. Rational meaning now we're looking to create that square root, that radical form, and put it into an exponent. If you have to go downstairs to get outside, then that means that 3 is the downstairs number, x to the 2/3. That negative 2 is kind of hanging out because the x is the only thing that the fractional exponent is touching. Downstairs to get outside. Here, everything is underneath, but if you notice, only the y is touching the 5. So I have kind of, if you want to think of it like this, which might be a little bit strange, but that 5 is only touching the y. So when we go to write this, I'm going to have 9 to the 1/2 power, because there's really a 1 on the 9, and a y to the 5/2 power. It looks a little bit goofy, but can you take 9 to the 1/2 number? 9's just a number. Plug it in. In your calculator, it'll tell you that it's 3, and you can't do anything with the y because it's a letter. All right, next one. 6 times 3/4. Well, seeing that I want it in rational form, I want the fractions, I'm going to go ahead and leave this. Times x to the, there's a 2 that's kind of understood there. Go downstairs to get outside. Let's see here. That means that 4/2, oh wait, I can do 4/2, that's just 2. So let's look at what we've got here. When I multiply like bases, I add the exponents. So if I were to add 2/1 to 3/4, let's see, I bet it would be 2 and 3/4, which is the fraction 8, 9, 10, 11/4. Also a little complex, but worth looking at. One story problem. All right, a sample of bacteria doubles each month. The expression 3,000 times 2 raised to the m power models a population of 3,000 bacteria after m months of growth. We want to evaluate the expression for m equaling -2, m equaling 0, and m equaling 3. Evaluate means to plug it in. So let's try it here. 3,000 times 2 to the -2nd power. Well, I know that negative exponents make fractions. The only thing the -2 is touching is that +2, so the 3,000 is staying and the 2 to its exponent is dropping. So it's 3,000 divided by 2 to the 2nd power is 4. I'm going to grab my calculator to divide it, and it ends up being 700 bacteria. M to the 0, so this one's 3,000 times 2 to the 0 power. Anything to the 0 power is 1, however the 0 is only touching the 2. So it's 3,000 times 1, which is 3,000. Lastly, 3,000 times 2 to the 3rd power. 2 to the 3rd power is 8. So 3,000 times 8 is 2,400. And this is bacteria as is this 3,000 over here. Describe what the value of the expression represents in the situation. Well, m equals -2 and m equals 0 and m equals 3. M is month. So how can I have -2 months? Well, if this is when the experiment started, sorry for the sloppy handwriting, then this must be 2 months before the experiment started. So this, m equaling 3, is 3 months after the experiment started. So the purpose of this particular type of experiment might have been, and I don't know if you can see the clip art underneath with the little petri dishes, but you could take like a Q-tip and swab it on something, and you could allow the bacteria to grow. What you'd be doing is you'd be measuring the growth. See all these little bacteria down under here? But just because I start the experiment on a particular day or on a particular month doesn't mean that there wasn't bacteria there before. It just means that at m equals 0 is when I started to watch its growth. So then the whole purpose of an experiment is to check that, well, after 1 month, after 2 months, after 3 months, after 4 months, how much bacteria was there. Well, the purpose of kind of writing an equation is that we can predict how much bacteria will be there. And that's where the second half of this unit is going, but for right now we're evaluating and describing what it means. Please let me know if you have any questions. Thank you so much.